Testing. Is this on? Can y'all hear me? Yep. All right. So JavaScript, eh? So my name is James Long. I work for Mozilla on a team called Apps Engineering, where we basically help developers write web apps. I'm the author of a JavaScript templating library called Nunjux. I just like to hack on stuff. I love doing the creative coding stuff, as mentioned in the last talk. I do all that day to day, but I'm actually going to talk to you about something a little bit different. I'm going to kind of talk to you about C. And it's actually really cool that you all clapped for that, because I thought all of you all would be like, whoa. But I'm not really going to talk about C as a language. I'm going to talk about C because this is really where it all started. So a few years ago, some guys got the idea of cross-compiling C and C++ apps to the web by actually cross-compiling the language C and C++ to JavaScript code that is executed on the web without any plugins. And this is really mind-blowing because it worked. Like, these geniuses figured out how to actually do this, and not only does it work, but it works really, really well. There's actually benefits to doing this, and it's not just the fact that we're too lazy and we don't want to rewrite it in JavaScript. So why would you want to even do this? There's just so many reasons. I mean, one is just that there's huge amounts of libraries in C and C++ that are battle-hardened, really complex libraries, and there's not really any reason to rewrite it. And so you get all that free. And there's other reasons too, like performance reasons, which are actually beneficial, which I'm about to go into. So I mean, how is so possible? Well, wow. There's a few really clever compilation techniques that made this possible, that were really, that those projects drove. But it really came down to a few key things. And one of the key things is that they figured out that you can actually work with 32-bit integers at the machine level in JavaScript. I mean, that's weird, right? But it turns out that in the spec, the bitwise OR operator says you have to return, the engine has to return a 32-bit integer. So if you do 4.6 bitwise OR 0, you get back 4. So it kind of looks like it's just rounding it down, but it's actually working with a 32-bit integer. So you can see if I pass this large number in, which is one number higher than 32 bits can represent, if it's signed, you get back, it rolls over and you get back the negative number, which is, 1, 0, 0, 0, 0, 0, 1 being the signed bit. So this is weird, right? I mean, there's even a way to do unsigned 32-bit integers with the triple bitwise right shift. I never know how to say that. Just this weird 3-arrow thing. So if you do -4, that shift to the 0, which should be a no-op, the engine will actually give you back an unsigned 32-bit integer, so you get back this really big number because -4. Those bits are basically, the bits are left intact. It's just about how the engine interprets those bits. So because of this one thing, it made it really easy to cross-compile like these large C and C++ code bases, because it's not slow to have to get the semantics of these machine types. It's actually pretty fast. And it's fast because not only is it using the real 32-bit int at the machine level, but with JITs that are all crazy these days in JavaScript engines, they can actually optimize 32-bit integers all the way through expressions. So if you have these two expressions, which if you do an addition and you do it with two ints, and then the result you want to be an integer as well, so I do a bitwise OR on the whole expression, you're using 32-bit ints all the way through, so there's no reason for the engine to convert this into a 32-bit int, and then back to a double, and then back to a 32-bit int. The JIT is able to figure out that these are all ints, and at the machine level, it uses 32-bit ints the whole way through. And you'll notice that I was very explicit on how I annotated this, and JITs, the whole reason for a JIT is that it can figure out the types. So there's a lot of places where it does this magically, and you don't even have to do it. But I'll go into why it's beneficial to do type annotations. And I forgot to mention, I'm sure all of you all know this, but the default number type in JavaScript is a double. That's like the most common conception. And it's true, but we have this crazy weird trick. So we get this like ability to run these apps. And we're used to generated code being slower than handwritten JS, right? Because typically languages have different runtime semantics, and so they have to inject different runtime code that is on top of JavaScript, and it incurs a small runtime performance. But with C and C++, they have little, if any, runtime. So there's really not much performance hit. And in fact, the only performance that it has is just the ability for JavaScript to execute this kind of code as fast as it possibly can. But if you compare the generated code from projects like Emscripten to the handwritten JS that you would have written if you had rewritten it from scratch, the generated code is actually faster. And there's really two main reasons for this. The first is that there's 100% type consistency. So since we're compiling these statically typed languages to JavaScript, we already know the types at compile time. And so as we're generating these ints and these doubles and anything else that we're doing, we're able to generate JavaScript that the variables and the functions never ever change the types. So if you say var x equals an integer, that variable x should never change type. So it's always referencing an integer. And the JavaScript engines with the JITs are able to do crazy good things with that and make sure that it generates very good code and that code stays in place. So if you change the type, sometimes it has to retrace the code and make sure that it can recompile good machine code. If you're changing types a lot, it just makes it slower. And the other big reason is that there's no garbage collection. So these languages, C and C++, are manually managed. So the way that they did that was they actually allocate this large typed array, and they're able to just, and pointers are just integers, right, into this large typed array. So the code that is generated by Emscripten manually manages this large typed array. There's zero garbage collection. There's zero JavaScript objects within this code. So if you spend all of your time in this code, it's actually never hitting the JavaScript garbage collector. So you get this predictable performance. So it's really interesting, right? Suddenly we're at the stage where we can cross-compile C, C++ apps to the web. It's kind of weird. I mean, just a few months ago, they were able to, I'm not sure if you saw this, but Mozilla was able to cross-compile the whole Unreal 3 engine onto the web. So there's millions and millions of lines of C and C++ code, and apparently it just took them a few weeks. And it blew the guys at Epic. Is that who makes it? It just blew them away. So it's interesting because we're suddenly seeing that this might be a viable platform in the future for compiling native apps. It's kind of a competitor to the Pinnacle because they're just similar goals. There are vast differences between them, and it still has kind of yet to be seen if the differences can be resolved. But I believe that the way this is heading, we haven't hit any brick walls yet that are large enough concerns to say, hey, this isn't possible. So instead of embedding a whole other thing into web browsers and convincing everybody to do it, this may be a more viable option. So there's several reasons. Some of you may not even be interested in this and wondering why the heck am I talking about C. But there's several people that I think are probably interested in this for things like games and number crunching, pretty much anything that's hammering the CPU. As seen in the last talk, you've seen that the WebGL is very, very fast, but the minute you start doing physics or physics engines in a big, complex 3D world, you're going to hit CPU limits. So JavaScript is missing several things, like 64-bit integers and 32-bit floats. We can't actually accurately get that yet. And SIMD and pthreads. Most of these things are coming. I actually meant to take pthreads off because it's probably just too controversial. I don't know about pthreads. That's probably not going to come, or at least for a while. But I'm guessing that we'll be able to, at some point, we're going to need to provide something that does something like that because I just don't see how we can't have something like it. I'm not qualified to speak about that at all. But the SIMD and 64-bit integers and the other types are coming with value objects. It's ES7, so it's quite a ways off. But fixing these issues piecemeal, I think, is definitely viable. So Mozilla sat down and saw that this was happening and saw that it was working really well. So about a year ago, they sat down and said, let's give this a name, and that's what asm.js is. This has kind of been a slow evolution. This isn't something just new that Mozilla just came up with out of the fly. So I think asm.js, as a name, asm.js has become somewhat overloaded. And I think it's kind of a good thing, but I think I just want to kind of clarify it. One thing is that people are saying, when they say asm.js, they really just mean asm.js style code. And what they mean is this code that pretty much just works with numbers. And there's some type annotations where you say pipe 0 when you want to work with a 32-bit integer. And you're just kind of having this like highly handwritten optimized loop. So it's slightly verbose, but it's not too bad, and the JIT can do a pretty good job with this. But what asm.js really is this spec. You can see at the meat of all of this is the same code as the last slide, but this is really meant to be compiler generated. There is this kind of boilerplate around it, which is defined in the asm.js spec, and it pretty much just helps set up the code. The first thing you'll notice is there's this use asm module, and it's kind of like a use strict. It pretty much just is a hint to the compiler saying, hey, I'm wanting this code to be this highly optimized subset. And there's a few other things about referencing the heap, so it actually in the spec says how you work with the large typed array so that it can optimize it out as much as possible. And then the other difference is you'll see every single expression is annotated with a type. So in asm.js, the bitwise or 0 means it's a 32-bit integer, and then if you have a plus in front of a variable, it means it's a double. And when you have 30-bit integers, it's really easy to get 8 and 16-bit integers. So that's pretty much what asm.js is. It's taking that code pattern that we saw that was working really well and was already really fast. We saw that there were even more optimizations that could happen if we kind of reified it into this actual thing. And it's somewhat controversial, but Firefox has been able to get a lot out of this because with relatively low man effort, we've been able to do this thing called AOT compiling, which is ahead of time compiling. It's relatively easy to integrate with existing JITs because it basically acts as if it's able to infer all the types like immediately. It doesn't have to run the code for a while and try to figure out the types. It knows all the types. So you basically annotate all of the code as if it was normal JavaScript with all the types and then pass it to your JIT to compile the code out to machine code. But you do this before the code is even run. So it's highly optimizable without much work because it knows all the types. It's reliable performance because it has this big blob of machine code that you're jumping right into when you call the code. So there's just a lot of subtle benefits to this. In Firefox, if you try to use asm.js and you don't conform to the spec, it will actually give you type errors. It will actually say, hey, this code is not valid as asm.js. So it's kind of like, hey, okay, you can't optimize it as much. And when you do compile it, it even tells you that it's successfully compiled the asm.js code. So that's what Firefox does currently. Chrome has definitely paid attention to asm.js. They haven't officially noticed the use asm directive, and that's a valid approach. They're just focusing on the asm.js style code and trying to optimize their JIT to make that work and taking every single edge case where it's really slow and optimizing the edge case. But the performance isn't quite as guaranteed. They've done an amazing job. I'm not putting down their efforts. But with a JIT, you just, if you're compiler generating it, then you're probably pretty good. But for people who are writing the compilers and maybe a new version comes out where they've changed the heuristics of the JIT, and it suddenly isn't JITted as well, the performance just isn't quite as guaranteed. So that's what Chrome is doing. And really, everybody should do this anyway. Mozilla is doing this as well. There's a bug that says the use asm shouldn't really affect the code at runtime. So there's all these bugs down here. You can see most of them are marked off. There's a few critical ones for typed arrays and stuff like that are going to add a lot more performance for code that's not in that specified use asm module, but is kind of asm.js-ish. So we want to optimize the code out more. But for the reason why the AOT is really interesting is because it's generating this big binary or this big machine code blob when it loads the JavaScript, it's able to do things like cache it. Just like it caches a .js file, when you load up the big Unreal 3 game that loads like 30 megabytes of JavaScript, if it's already cached that big AOT compiled binary blob of executable machine code, it can just load it up from cache and not have to re-download all of that JavaScript. So in this way, it's kind of a power-up for JavaScript. Did run, cool. So these are current benchmarks. I'm just going to kind of fly through these because I'm taking longer than I thought. So you can see Firefox is blue, Chrome is red, and green is native. So this is the time compared to native. So like you can see native is at the 1 time speed because it equals itself. So you can see Chrome has caught up pretty much. If you run anything of the use asm module, Firefox or Chrome, they've caught up, but these are micro benchmarks. They're smaller pieces of code that just benchmark certain things. If you look at more real-world benchmarks, Chrome still hasn't proven yet that they can get as good as we can with the AOT compilation strategy. You can see there's the Emscripten guys have actually compiled the Lua C code in Emscripten, so you can run Lua in the browser, and they're running all these tests of actual Lua code and timing how much that's taking. And there's just a bunch of other. Bullet is a physics engine. Box2D is also a physics engine. So they've caught up on zlib. But there's just all these edge cases where they haven't been able to guarantee the same performance. So that's asm.js. It's really hard. It's really easy to not understand that. You kind of have to see the whole evolution. It's a slow evolution. We're not saying we're going to add this huge thing to our engine. And you really, you could handwrite it, but there's really most of the performance benefits are going to be for large code bases, and you don't want to handwrite a lot of large code like this. It's just not fun to handwrite it. So there are a few ways you can use it. One is to use the project Emscripten, which I've mentioned. It's a C++, or it's the LLVM compiler, and you can write C and C++ and compile it through that. This really is the preferred method. I mean, most of this is going to be used for native apps that are already large C and C++, like games and stuff. It's battle hardened. I mean, like I said, they've been compiling things like the Unreal 3 engine, and it's been working great. Lots of people are compiling all their games and running it on the web. But about a year ago, another project that came out of the Mozilla research group was LLJS, and it's called Low-Level JavaScript. It was released, and as far as I know, after it was released, they kind of stopped working on it. And it was just this kind of interesting, fun experiment. It adds bits of C to JavaScript. So essentially there's optional C-like types and manual memory management. And I got involved with this several months after they released it because I saw nothing was really being done. I was interested in it, so I just started playing around with it. So here's an example. Looks very much like C, as you can see. You have pointers. So by default, right now it actually forces block scoping onto you, which I think is probably a mistake. I think we should change that. But it forces you to use let. So the idea is you can go into existing JavaScript code and add these types. So that's why instead of just int x, it's let int x. So you have these pointers. You can see you can take the pointer value of an existing variable, and then you can dereference it. So at the end of all this code, x equals 10. I'm not going to go into C, but if you know C, you're familiar with all this. You can have functions, of course. Stack allocated data. So basically, I'm stack allocating an array of ints right here of 1,000. And what's happening here is the compiler is actually taking it. It's using the same technique as Emscripten does, where there's a big typed array of memory. So as I stack allocate, because I know the type at compile time, this all the way out, there's a stack pointer when it compiles out. And basically, I'm trying to say, there's absolutely no garbage collection here. This is all on the stack. It's all just typed array reads and writes. And I can pass the array into this function because it's just an integer, it's just a pointer, and I can do stuff like this. So I'm going to kind of skip over this, but you have structs like in C, but we added this like constructor function because that's always a big pain in C. And you can see you can make a vector point, and you can do stuff with it, and you can cast things to ints. So doubles and ints are casted. So if you cast a double to an int, it's already rounded down. So this is kind of in flux. This isn't a big library at all. Like it's just me working on it on the side, kind of. This isn't a big thing Mozilla's releasing. We're just kind of enjoying it, and I've been meaning to talk to more guys at Mozilla to see what they think we should change in the language. There's probably a lot that's going to change. But this is hopefully letting you guys get access to stuff like asm.js without having to write C. That's kind of the goal. And that kind of brings me to this point, which there's optional typing. So this is just normal JavaScript, right? You can just like have your canvas and your context and your function render, which renders little pretty squares. But if you wanted to do some really heavy physics calculations on it, you could do it right here. So you can optionally mark points as a vector of these vec2s up here, and then you can do some heavy processing right here. But then down here, you can just render it in the context and access this array. And this will all compile out to the typed array reads and writes. So it's JavaScript meshed with C, and it's really interesting. This can't compile out to an actual asm.js module. This just injects that asm.js style code in the middle of JavaScript, which is still fast. Let's see. So let's just kind of, that was was supposed to be a quick introduction to LLJS. Let's just say that you want to build a vector class. In JavaScript right now, if you do that, you kind of, some people just use objects, right? You have objects with x and y. And then you reference that as .x and .y. But you're hitting the garbage collector a lot. If you're doing a lot of stuff and with a lot of vectors, you're hitting the garbage collector a lot, and every single .x and .y is a property reference, and that potentially could be slow. JITs, of course, could optimize this out, but there are still cases where it just is too much. There's a little bit of overhead with that. So some people do this where they use an actual array, but that's kind of ugly because then you're always referencing it x and y as 0 and 1. So there's this library GL matrix. I'm sure a lot of you know about it. It's a great library, but this is what the internal code looks like. And if you want to, it essentially works with raw typed arrays. And if you want to use any of the values like a 3x3 matrix, it's just terribly ugly. So this is what an LLJS vector looks like. You say struct vec2, and then you can access it with point.x and point.y. This is all stack allocated, so this just compiles out to this. So this is compile code. This is never hitting the GC. It just basically reserved 16 bits because I use a double, which is a double x and y, which are 8 bits of floating point values each. So it increased the stack pointer by 16, and then it references the x value here and then the y value here. So the stack pointer and then stack pointer plus 8. And then you return by just reading from the typed array. So this is just really fast stuff. If you're doing a lot of vector operations, this is the kind of code that you might want to generate. So this is a similar thing. You can, if everything is stack allocated, this compound expression will compile all the way out. So pointers, you have pointers and all that stuff. I'm going to kind of skim over that. This is the internal memory representation. So one big thing, in the first value there's a heap pointer, in the second value there's a stack pointer. Heap and stack on the other lines, and they grow together. You know what I'm talking about if you do. If you don't, then I'm not going to go into it. So this is the compile code. You can see that it decreased the stack pointer. So just going to kind of skim through this. What's interesting is that it uses Esprima. It's not like some crazy weird compiler. It's very much JavaScript with type annotations. So it uses Esprima with some patches. It just went into Esprima and just actually added some type nodes and like the ty property on the node, so every single node can have a type. And so there's several phases that the compiler goes through. It parses it with that version of Esprima. It lifts it. ESTransform is a really cool library that makes it easy to work with AST nodes. Then it resolves the types. So if you have type defs or structs, it resolves everything correctly. Transforms it, and then it lowers it, which does type coercions. Then it generates it with ESCodeGen. So it's very much all of the libraries that we're used to using as a JavaScript. I'll just kind of skim over this, but ESTransform is a great library. You can, you know what, I'm running out of time. So what were we talking about asm.js? So this is where I came in because they wrote this thing, LLJS, before asm.js was ever a thing. And then it was kind of abandoned. And they came out with asm.js. And I was like, well, obviously we should want LLJS to compile asm.js. So earlier this year, when I was alone in a hotel room, totally bored, I was just like, oh, I'm going to do this. So I took their code and I just hacked it up. It's really bad. And now it generates asm.js valid code. So there's kind of two versions. There's this pure LLJS module, which can actually generate that module, that asm.js module, with that kind of boilerplate that tells the browser a hint. And then there's that mix LLJS where you can write JavaScript and the optional types, which can't generate the actual asm.js, but it generates that style of code. Things are very buggy right now. There are things you can't pass certain types or as certain stack allocated stuff, and you'll hit this weird error, especially in the mix mode, because I focused on the strict mode, and I never really went back to fix the mix mode. This is all just, we're just having fun. At least I am. I don't know if you guys are. So what I did is I forced type annotations on every expressions to make it asm.js available. Wrap code in the asm.js boilerplate, and I just fixed a lot of stuff. So if you want to use it, this is my fork, jlongster/LLJS. How you invoke the code in the mix module is you just call LLJC on it. If you want to generate an asm.js module, you pass -a, and then -m is the module it should point to that you can call. And then -e are the exported functions that you want to export. The original creator was Michael Bebenita and Shu, another guy at Mozilla, and their fork is that's the original code is at their repo. So there's a minefield of bugs. If you try to use this, you'll probably blow your arm off. Dynamic allocation is something I haven't done yet. It was in the original LLJS, but I haven't ported it into the asm.js version. So you should be able to say new point and then use that point, but you can't do that yet. Source maps are an obvious thing. Then you could step through in the browser. Much better integration between the mixed and pure LLJS modes would be really interesting. And probably rethink some of the language features too. And the integration between the mixed and pure LLJS modes is interesting to me too, because it actually is possible that what this becomes is purely the mixed mode, and what you use it as an integration for mscript and compiled stuff. So if you compile the big C++ engine onto the web, maybe you could use LLJS to actually extract the C types, like the vector type that engine uses, and then you could write that vector type throughout your JavaScript code and call into the engine, and it would be really interesting to do that. So yes, I have 3 minutes for demos. So if you didn't care about any of that, then I'll show you some pretty stuff, because this is supposed to be a graphics thing. I just added WebGL to the title. This does use WebGL, but it's just not the absolute focus. Because again, if your app is mostly GPU bound, this isn't going to help you much. But it's interesting because most things that are CPU bound most of them tend to be visual stuff. So this is really, let me run this thing. So this is a cloth demo that I made several months ago to test out to make sure this is working. Localhost. Hope it works. Oh, shoot, that's the wrong one. Hold on. Let me just kill that and go back to here. Yeah, it was just a cache problem. So this is a cloth demo. Oh, man. Oh, sweet. So you can kind of drag this cloth around. It's really fluid and really cool. So this uses Verilette integration to do the forces. And you can tear it by right-clicking. It's just kind of this fun demo. So this is all written in LLJS to do the processing part of it. I can increase the cloth, make it really heavy. So it's actually really annoying to deal with a heavy cloth because it takes it's much more sensitive to the parameters. So this is as high as it goes. I don't even know how big this is. But it almost looks like a water. I mean, my physics is obviously not very good. But you can tear it. So this is running around 20 milliseconds. I'm not going to pull it up in Chrome, but it runs about 35. So this kind of code is the asm.js. It's just so heavy. So I just want to show you just one thing real quickly, if I can. Run. And that's, so basically I call cloth.renderLines. What cloth is the actual LLJS module. It has this render line, so I stack allocate a ton of ints because I don't have dynamic allocation yet. And then I render I get all of the points that are valid, and then you can see that I return this int. So I'm casting verts, which is an array, to an int. So I'm actually passing back a pointer to my JavaScript code. So I get a pointer, and then I do this really hacky thing where I get a reference to the big typed array, and then I call subarray, which doesn't, it just gives me a new typed array, or it gives me a new view back on that typed array. So there's no new allocation, but I just kind of get this thing. This gives me back a float 32 array thing that I can pass to WebGL. 2 more demos, please. I'm not going to talk any more tech stuff. Okay. So, and then I noticed it was really cool. Notch, the creator of Minecraft, came out with this demo a while back where he did this, and it was like this crazy compact 100-line JavaScript file. So I ported this to LLJS. So this is running with asm.js. If I try the without asm.js version, it's a lot slower, and then you can try the reference file too. So the interesting thing is Notch's code was really hand optimized. It always uses floats. But there's all these places where you want to use a 2D vector. He was obviously saying like px and py for points. But this, when you use LLJS, you can say p.x and p.y, and know it's just going to compile out to that typed array. So one more really, really, really fast thing, which is that same demo, except the neat thing that is a benefit over mscripting is that I can pull up a live editor. So this is the actual LLJS code. And I can be like, oh, you know, I'll just pull up the LLJS compiler and throw it in here and call it .compile, and then just call it eval on it. I mean, why not, right? So like with this really short line of code, I can be like, what happens here? And I have no idea what this is doing because I don't, and it shows an error down there. Oh, I see. So I can. It's really easy to, so this is the asm.js code that it compiles to. Really crazy stuff. But you can look back here. It's like, whoa, that's kind of neat. And I can just change all these parameters. But what's really neat is that you can't, like, I'm live editing this, and it's even when you call eval with use asm, Firefox will AOT that really fast code. And this live editing stuff is the stuff that's just going to be hard to do with stuff like mscripting. You could do it when you cross-compile the compiler into the browser, but this is just a really simple .js file that is just a really simple compiler that you can load to write this kind of code. So that's really fun. So that's all I have for you.